Okay, we start up. So the camera fainted during the last minutes for the last exercise. So it should be a green light and a red rec there. Okay. Yell out if it stops. I don't know why he fainted. Anyhow, before we begin, any questions from any of you? As you all know, hopefully, we have extended the deadline for exercise 2 1 week. And then after the deadline, you will then be given your first report exercise. Coming back to that one later. One thing that I am a little curious about, that is this class list. I guess you guys, you don't have access to this list at all. Where do we have it? Users. Here we are. So here, for now, we have 64 students. Okay. But I mean, this list is not accurate, it's not precise, it's just an internal list anyway. So a lot of you students, you sort of try different courses, and then by the 15th of September, you are sort of have to choose which course are you actually going to take. Meaning, this list is never accurate. But when I'm going to create groups for the report exercises, I'm going to use this list and then randomly pick 3 students and make a group. Then it would be nice to know that this list is, well, as exact as possible, or else I will create group with only 1 student or 0 students. So what I'm planning to do, I'll make a copy of this list and then put it out on your Blackboard homepage. Then if you know anybody who has quit, who shouldn't be on the list, then please tell me, so I can get this list as accurate as possible. That would be very nice. So I will fix that one soon. Okay. So no questions? Then I will continue where we left off the last time. We're playing around with the square cavity case, but we try to change it into a turbulent case. So let's see how far we got. Let's see now. Yeah, we did one simulation here. Let's have a look at it. Parafoam. And apply. Let's just look at the mesh first. This was what we were also attempting to do, to stretch the mesh in Turbulence, and here with quite a low Reynolds number, it's turbulent, 10,000, but just turbulent. Then it should be possible to resolve the boundary layers close to the wall. And one way to do this that was to stretch the mesh so you have smaller cells towards the wall. So we got that far. But when we started plotting our solutions here, let's see now, we have velocity, and then we take it to the end. We have something like this. And this is frankly not really trustworthy. So we should get sort of a big vortex here, but he has trouble getting the fluid moving, obviously. And and also the solution didn't converge. Also something to be worried about. The pressure, well, something strange up in the top right corner, else nothing much. And then the turbulent parameters, they became something like this. There's only some action at the top, and especially at the top right corner for k and epsilon. So no, we don't trust this solution. So let's get rid of it. That was foam list times minus remove. And then let's have a look at our setup. Gedit, where should we start? Well, we have this file in the constant folder. In my version, it's called Turbulence Properties. So what did we do? Yes, we did use the k epsilon. Okay, fair enough. And what else did we do? Well, in the 0 folders, we put for the turbulent quantities. We now used the natural boundary conditions for turbulence. Fixed value and a very small number on all the walls. And that should be, say, appropriate. Now I think this number here, 0.3, is a little bit too high, so let's make it a little smaller. It shouldn't change much. This is just the startup values anyway. He should find the solution in the end, so, but he might find it a little faster. Let's have a look at the epsilon. Sen goes here, natural boundary conditions. We are supposed to resolve the boundary layer. And again, this value is way too big, I think. Let's put a smaller number here, something like that. But as a first remedy now to get a better solution, let's have a look at the mesh. Here I have 20 by 20 cells. And now this little advanced stretching thing, so I can resolve the boundary layer. Let's go to 100, 100. And see if that one helps. So now I have to do the mesh again. Block mesh, like that. And then we run simple foam. So the theory for simple foam, you give him a big number of iterations in pseudo time, and then hopefully he should stop automatically when he finds a converged solution. And this one doesn't look good. He doesn't want to stop. If you want to check your simulation while running, you can freeze the screen by Ctrl S. And then just have a look, how far have I got, how is the residual look like. Well, actually they're quite small. Well, the epsilon, he struggles a little bit. So Ctrl S freezes the output, Ctrl Q continues. So Ctrl S, Ctrl Q, that's a nice one. No, he didn't find a solution within 2000 iterations. So actually, it doesn't look too good, does it? Now, let's have a check also for the y plus values. I had to write simple foam, and then it was minus post process, and then minus func y plus, something like that. Now, this one looks very nice. I have very small values for y plus, below 6. This means I have resolved the boundary layer. You must be below 6. And I'm well below 6 here. With 100 by 100 mesh and stretched, yeah. And also not that big Reynolds number. This one should be much better. Let's try that one. Parafoam. And we apply, and we go to the end, and we look at the velocity. Well, it's getting better. Now at least something is happening here. Yes, we get a nice vortex. Looks promising. Then let us have a look at the turbulent thing. Nah, I don't trust this one. He produces the turbulence. They have quite high values up here and in the corner and a little bit down here. Values not too big. Well, they shouldn't be anyway, but we don't get a transport of the turbulent K inside our domain. I don't believe this solution at all. Same goes for the epsilon. So no, this is not good. But I mean, we have done everything right, haven't we? But what should we then do? We change the turbulence model. Now I've done the standard K epsilon. What's wrong with the standard K epsilon? Something he doesn't like. Well, he doesn't like low Reynolds number problems. It's a high Reynolds number model. Furthermore, he is best for external flows, flow around buildings, stuff like that, not internal flows. So the K epsilon is probably a bad idea. We have one, it's called realizable K epsilon. A little bit more modern, a little bit more advanced. We can quickly try it. Shouldn't take too long. Let's see now, we have the result folders. Well, he's going to overwrite them anyway. Simple form. No, he doesn't seem to stop either, does he? No. Residuals are quite small actually, but let's go all the way. We are closing in 1800, 19, 2000. So the final residuals, yeah, looks okay. Epsilon, they're quite small actually. So obviously here the demand for a converged solution is quite strict. So if I had smoothed it up a little bit, yeah, then I could probably have gotten a say converged solution earlier, but okay, I want to keep it strict here anyway. Let's just have a control here over the y plus. Yeah, they are still small. Looks okay. Let's have a look at the solution now. More modern K epsilon. Go to the end, velocity. That one looks better. That one looks better, doesn't it? So now we have a big, nice vortex here, and I think also we should have sub-vortexes down here, and even a vortex up here, as we should. So now this one looks much more promising, I would say. Now for the turbulence. What do you know? I don't trust it. I don't believe it. This can't be right. No, the epsilon. Now we take that turbulence model and we throw it out the window. So what then do we do? First of all, let's get rid of these solutions. Then let's take another one. What do we have here? K omega, why not? Let's try that one. Save. And if I try to run that one, I think he will crash because I haven't changed the 0 omega file. Simple form. Yeah, fatal error. The people who wrote open form, they are sort of a little bit dramatic. So it's a fatal error. Your PC is about to crash or start burning or something. It's not that hard. This is quite normal. So what does he say? Cannot find patch field entry for moving wall in the file 0 omega. No surprise. So I have to edit that one. Shouldn't be too hard. Let's see, where were we? 0 folder. Because so far I only use K and epsilon, and also new T. But now I have to edit this one as well. So you see, this was the standard setup for the pitch daily case with an inlet, outlet, upper wall and lower wall. Now we don't have that. So what should we use here? Well, we can have moving wall, was it? Moving wall. And then we have not an outlet, we had fixed walls, like that. Then I want to have the same type here. Let's see now, copy these two, and I glue them in here. So it's a fixed value, but the omega, he has a nice way of calculating a value. Just uses the internal field to evaluate it on the border. So that's nice. I don't need the upper wall and lower wall, so I can delete those. I don't have them. So now we should be good to go. Okay, let's try again. Simple foam. Yeah, he runs. Now let's see if he stops. Doesn't look too good. 500. Ah, he stopped. 620. Wow. Success. What about the residuals? Yeah, quite small. So now he has, according to him, found a solution which he accepts. Let's just check the Y plus. What do you know? This doesn't make sense. 50, 40, 50. And here on average 6 on the fixed walls. Doesn't make sense. I don't trust this solution anymore. Let's have a look at it. Paraform. Go to the end and we look at the velocity. No, I don't believe that solution. Definitely not. So the top wall is running and the rest of the fluid is almost standing still. No, no, no. And the K, this is just rubbish, only action at the top wall. What about the omega? No, doesn't make sense. No turbulence inside the field at all. Let's throw this one away as well. Okay, so be it. Remove those. Then we have one more. K omega SST. Must be the last attempt that we have here. What was the K omega SST? That was a mix between the K omega and the K epsilon model. He uses K omega close to the walls, and then he uses K epsilon sort of in the internal field. And he found a solution now already after 386. Residuals are small. What about Y plus? What about Y plus? Yeah, now we're talking. They look very small and nice. Parafoam. Go to the end and then look at, say, velocity. Now we're talking. Now we're talking. We get a big vortex, as we should. Probably the small secondary vortexes as well. But have a look at the turbulence now. Oh yes, now we're talking. Now we're talking. So this is a solution I can trust. Omega, well, he's a little weed, and what it is physical is a sort of a turbulent frequency or something like that, so he's not so easy to understand physically. So I don't really care about him. But the K, turbulent kinetic energy, this one really makes sense. Yes, we have a lot of activity at the top wall, of course, and then he will be transported and say the layers here to the walls with a driving vortex in the center. Of course, you will have a nice shear in this region. So this solution I can start to trust. But before you open the champagne for this one, what do you have to do? You have to validate and verify your simulation somehow. Meaning, now I should go on the internet, find somebody that has either done experiments on this case, Reynolds number 10,000, or if they have some very accurate simulations, so I have something to compare with. I sort of have to prove that yes, this solution is trustworthy. So that is something yet to come in this course. It's quite essential actually to really make your simulation trustworthy. So I would say this looks promising, but we can't really conclude that this is the gospel truth. It doesn't have to be. It can still be a little bit wrong. So, but anyhow, I think this one, at least from all the versions we have tried so far, this one definitely is the best. Okay, any questions to that one? Yeah.
What does omega represent?
Sorry, what was?
Omega.
What it was? What it is? Well, by dimension is a frequency. But I mean, it's evaluated from, I think it's k squared by epsilon, something like that, by definition. So physically, what that means, don't ask me. I don't know. It really doesn't make any sense physically. But think of it as just one turbulent quantity. So together with k, also a turbulent quantity, we have those two that we can sort of play around with. And as long as they describe the turbulence, we are happy. But I mean, in the end, the detail for an omega and physically what it means, we don't really have to worry about that. The K is a little bit more easy to understand, the kinetic energy of the turbulent motion. That makes more, say, physical sense. But the omega, don't try too much to grasp what the heck it is. I will strip down this case and put it out on the home page for you, so you can have a look at it and maybe have some advantages and use it later. Okay, that was square cavity turbulent case. Now I want to have a look at inlet values. Now let's see, here we have something. This is something that I wrote from the Introduction to CFD course. So I'll go through this. I'll put this out for you as well on the home page, so you could use it later. So say now you want to have an inlet, but the inlet should be a fully developed velocity profile. So we're looking at a laminar problem here now. And what I want to have a fully developed laminar flow from a plate to a symmetry line. And it's not a pipe, it's just an 2D of an infinite plate here. So what will the solution be? Fully developed flow. You should remember that one from kindergarten. You send in a constant velocity if you say 1. What's the maximum velocity here? 1. Come on, you can't be 1. If this is 1 and that one also was 1, then continuity fails. So the area under the curve here should be the same as the area under the curve here. Don't you remember? Okay, then everybody out and you take fluid 1 again. Come on. For pipe flow, you remember, I guess. Not even there. You're in trouble, folks. In pipe flow, the maximum velocity for laminar flow will be twice the average. Between two parallel plates, 1.5. So the correct analytical solution in the center should be 1.5. And then you have the Poisson parabola as a solution. Now I want that one as an inlet. Of course, one way to achieve it, if I have an inlet and then this one on the right here, maybe a large room or whatever, doesn't matter, but this should be my inlet. Of course, you can just extend your inlet area to a long x direction and then send in a constant velocity and let the flow develop naturally. You can do that. What do you call this length when you go from a constant profile to a fully developed profile, either along a plate or in a pipe or whatever? Remember what it was called?
Entry length.
There we have the entrance length, correct. And you find formulas, how long is this entrance length? Typically laminar, 5% of the Reynolds number. When you have it non-dimensional with the opening here. But that means this area here, it can be pretty long. So that can be expensive and also unnecessary. It should be possible to put this velocity profile as an input value. If you look at the input value in Pitts Daly, let's see here, where do we have it? Pitts Daly should be here, 0 U. You see they send in a constant value of 10 meters per second. And this was then the backward facing step. So just a constant value, obviously not correct. So here they should have a function, a velocity profile. How to do that? Well, we have a recipe here how this one is done. So I have sort of created a setup case here for you. I call it just in one. And that is a simple form, but a laminar case. Simple form is built for steady state solution, turbulent flow. But yes, you can actually go to the model here. If I now just write simulation type, if I wrote laminar here, he won't look at the turbulence at all. He will simulate it as a laminar case, no problem. And then you don't need all these 0, k, epsilon, omega files at all. You only need the velocity u and the pressure p. So yes, it's possible to do that. It's possible to do that. So when you run this setup case, or the way I've set it up, it's the geometry here, but I've done it very easy. Sort of set in a square domain, and then I use cyclic boundary conditions for the velocity. What do we mean cyclic? That means when he wants to put a velocity at the outlet here, he goes to the inlet and uses the same value he finds here, or actually in the first cell. Same as the inlet, he will then, as a value here, he will take the value he finds on the same location at the outlet. So they are sort of matched. You can think of it as if you had an infinitely long, say, x direction here. So we just take an arbitrary section of it. So whatever comes in equals what goes out. So we use cyclic boundary conditions there. Okay, that's for the velocity. Now, what about the pressure? We are going to need a driving force in this problem. Something has to move the fluid. And here, I just took it crudely and set up a pressure here, a constant pressure, P1, bigger than the constant pressure P2 on the other side. So a pressure difference, there you have a driving force. And since I know the analytical solution here, then I know what this pressure difference should be, depending on the length, of course. I think that I choose the length 1 meters to make it easy. So then, simulate. And then we have something here. And this one, also something that we are going to use now in the future. How is open foam organized? So let us just do a simple sketch here. And here I have 2 by 2 cells, just for simplicity. Open foam. Uses co-located cells. What does that mean? That means all your unknowns, velocity, pressure, turbulent quantities, whatever, everything is located in the cell centers. So here you find the pressure, you find a u velocity, and you find a v velocity, and you find k and epsilon and omega, whatever. So in all the cell centers, that is where your unknown is located and calculated, like that. What about the boundary? We need boundary values as well. So then you can think of sort of an infinitely thin little layer inside the wall here. So yes, we have some boundary points here as well. And here, and then down here as well. So these are for the boundary conditions. So you have boundary points and internal cell points. Just do it like that, boundary points. So this is how OpenFOAM operates. And actually the mesh doesn't have to be squares like this or rectangles. It can actually have any number of faces. So this could be a computational cell in OpenFOAM. So you can have many, many faces around one single cell or element or whatever you want to call it. But the same applies. You will have your velocities and the pressure in the cell center. It doesn't really matter how many you have. So yes, we can have quite messy mesh systems. We're coming back to that one later in this course. And also here, if this one was a boundary, then yes, you also need a boundary point here as well on that face. The problem is now, later after you have done a simulation, you have some results and you want to use them, you want to make a plot. Then maybe ParaFoam is not, or ParaView is not the best program. You want to take the data and plot it in MATLAB or Python or whatever. And maybe there compare with somebody else's data or whatever. How can you find then both velocity, pressure, turbulent quantities, and the location of these points? That's the problem. That's not so easy. But here you have a function, right cell centrus. It's a British guy who has written this script, so it's written in the British way with a center, centrus. I think it's pronounced centers, but never mind. So that one will produce the 4 files. A C file, he will then take the entire domain, and then you have only X positions, Y positions, and Z positions for your mesh system. We can try it quite rapidly. Let's see now. Where are we here? In the, well, that was a cavity case. We had 100 by 100 cells. Okay, let's try this command. So the syntax here for your version of OpenFOAM, I don't know. But if you write in Google OpenFOAM, write cell centers, you should find annotation that should work. So let's try that one, post process, and then it was, what was it, minus latest time, minus latest time. I mean, if you don't write latest time, he'd do it for all time steps, but I mean, that's not necessary. It's the same mesh for all times anyway, so I only need one of these. And then it was minus func, and then it was cell, no, it was right cell centers, wasn't it? Yeah. The function right cell centers. There we go. So now he has created some files, a C file, a CX file, CY, and CZ, only for the latest time. So where is them? Where do we find these files? Well, 386 was the latest one. There you have them. So under the last result folders, you have received these 4 files. And yes, you can have a look at them. One important thing there. Open. Let's go to the system and the big boss file, the control dict. If this one, write format, doesn't read ASCII, if it's binary, then you can't read these files. It's only OpenFOAM that can read them. So yes, it has to be ASCII. But now that means we should be able to open these files. Let's have a look at them. The C file. Here you have it. So it's a sort of the same standard setup for OpenFOAM, C++ syntax. So here you have internal field, non-uniform list as a vector. So you have 10,000 points, and you have X, Y, and Z position for all the centers. Okay, fair enough. And at the bottom, oh, let's go to the bottom. Come on, all the way down, 10,000. But here we have something. Whoops. Not so easy to get. Here we are. So first he comes with the 10,000, but that's only the internal. Then he comes for your boundary points. And yes, I have 300 along the fixed walls. 300? Well, remember the case now is 100 by 100. And fixed walls, I had 3 of them. Hence, yes, I will have 300. So here I have the location for the different boundary points along the walls, the fixed walls. And then up, not page up, come on. Stupid program. Where are we? Front and back is empty, yeah. We should have the moving wall here as well somewhere. There it was. Moving wall. No, that was fixed wall. Here it is. Moving wall. The top wall, here you have the location. Yes, I only have 100 of them. So you see the X position is increasing, Y position is constant equal 1 at the top. Of course it is. And the Z, yes, of course, he's constant all over the place. So there you have it. Now if you only need, say, the X position, then you only need one of these files here. This is also a non-uniform list, but it's not a vector, it's a scalar, only one number, only X positions. But the format, the logic will be exactly the same. So these files, these are something you can use for two purposes. One purpose would be now you have the location, and then you can use this location in MATLAB or whatever to plot your results. And another thing, how do we know how OpenFOAM organizes its cells? Which is cell number 1, 2, 3, 4? We don't know. And for, say, a little crazy mesh, this one can be pretty random. But the sequence here will be exactly as the same sequence when you have the results. Then you can, for number 1, 2, 3, then you can find velocity number 1, 2, 3, or pressure number 1, 2, 3, if you go to the result files. So if you look at the result here, velocity, for instance, you see it's exactly on the same form. 10,000 numbers for all the internal velocities. U, V, and W. It's a vector. But now you know exactly where they are located. It's the exact same sequence. So that is the way to have both positions and your physical values, the results. Okay. So here, I'll just show you. I did it very simple here for this case, 5 by 5 cells, just to make it easy. So yeah, there you see the inlet here. It's only 5 points. And then same for the outlet. And then I could load these values directly into a MATLAB script. Now I wanted to create a fully developed velocity profile. Well, then you have the formula here for the analytical solution, fully developed flow. And then I just create a file and write out the velocities. So here are the analytical velocities from 0 and then up to 1.5. But I mean, you have half a cell from the wall and the symmetry line at the top here. Now I want to use this one as a boundary condition in OpenFOAM. How to do that? Well, here is a 0U file, and then you see what you can do. At the inlet, I now have a fixed value, but it's not one single number. It is a non-uniform list with a vector. So then you just punch in or glue in all your velocity values at the inlet. The outlet and the walls and whatever, they are as before. So that is one way you can sort of punch in a given velocity profile or a given K profile, omega profile, whatever you want. You can do it in this manner. I'll put out this one for you. So you have you have the setup here for the case that can be run, and even this little MATLAB script. So you'll find that one in on the home page pretty soon. Any questions? Yeah.
How to know in which order it will be applied? Like if the cell are going to, if the velocity profile is going to be like that or like that?
Yeah, that's the whole point. That's why you have to look at these C files. He will give you the correct sequence. And I mean, for a rectangular cell, normally he will start at the bottom left corner and then go up. But we don't know, does he go first in the x direction like that, or in the y direction like that? We don't know. And he can do whatever he wants. And when we have a more complex mesh system, it can be pretty random actually. So it's quite essential to have these C files, to have the correct sequence. Very important. Other questions? Let's take a break.